Hi everybody. We're going to talk a bit about extreme value of functions today. As we get into that, we're going to need to define a few things, so we'll start with some of that. First big statement will be what we call absolute maximum minimum values. Absolute maximum values. So what an absolute maximum is sort of as the description says, would be the highest point in the function. Or if you were to graph the function, the highest point in a graph. You would define that as a function f of x has an absolute maximum value at x equals c if for its entire domain f of c is greater than f of x. Basically saying that that's the highest point in the whole setup. Similarly, the condition for an absolute minimum value is the same as above, except f of c is less than all other f of x. Should have equal signs in there because the c is part of the domain. So basically on a graph we're talking about the highest point on a graph or the lowest point on a graph. You already talked about a special case of these when you're looking at quadratic functions. You refer to it as the vertex. In a standard quadratic that hasn't been reflected, the vertex would be the absolute minimum value of the function. Um, so if you had a basic sort of quadratic, the vertex would be its absolute minimum. Um, it's worth noting that sometimes these are referred to as global maximum or minimum values. And collectively, maximum minimum values are referred to as extreme values or extrema. Actually, maximum and minimum values referred to as extreme values or extrema. Now, a couple of other definitions. We can also talk about local maximum and minimum values. And in those cases, it's the same sort of condition as the absolute ones, only instead of being over the entire domain, it's just for some small section of the domain. Local maximum minimum values are the same as their absolute counterparts. Only the inequality hold for a small portion of the domain. So for instance, if I gave myself kind of a funky looking polynomial sort of shape here, say something like this, which carries on. Note the way that I've drawn this, that this function would have no absolute maximum or minimum values. The function keeps continuing this way, so there's not going to be any one point that's bigger than the rest of the graph. And it also continues this way, so there's not going to be any one point that's lower than the rest of the graph. However, I do have some absolute maximum value, or some local maximas, and some local minimas. Minima, I suppose. Oh, and I lost that on the page. Very technical here. Well, I didn't even have to cross it all out anyway, so local minima. Alright, so those are some of our basic definitions. We've got a couple more points to talk about here, but largely these are extreme values of functions. Low points and high points, basically. So I will carry on. With a few more things to define, although I've got a theorem to break into here, which is not a particularly deep theorem. It's called the extreme value theorem. And when you think about it, it's going to sound more like a mathematical statement of common sense than anything else. The extreme value theorem just states that any function f of x that is continuous on a closed domain must have an absolute maximum and minimum in that domain. So nothing particularly deep about this. Basically, if I draw a graph that has two fixed endpoints and is continuous everywhere, then there's got to be some point that's the highest point, and there has to be some point that's the lowest point. Basically, is all the extreme value theorem says. All right, a couple of more things to define, and then a few conditions relating all these things that we talk about. Critical points. Critical point. A critical point on a function of x is any value of x where your derivative is equal to 0 or your derivative does not exist. So those are critical points, places where either your derivative is equal to 0 or the derivative does not exist. And a subset of that group is what's called a stationary point. And a stationary point on a function f of x is a point prime of x equals 0, or the derivative equals 0. This makes a lot of sense when you think about it in a physics sense, because you think about a moving object, and if you look at a graph of its position, where the derivative of that graph would equal 0 is where your velocity would equal 0. It's where you'd stop moving for a moment. If you thought about a graph of an object that was thrown up in the air, which would form a parabola, and the high point of that parabola would be where it would start to turn around and come back down to Earth. Stationary point. All right, a few statements of connection between all these things. First out, all absolute extrema are also local extrema. Because obviously, if it is the highest point on the entire graph, then it's going to be the highest point in its neighborhood, in its local area on the graph. Same thing for low values or minimum. All stationary points are critical points. But in each case, the opposite is not true. All local extrema are not necessarily absolute extrema. All critical points are not necessarily stationary points. And this last one is more a statement of where you can find, so I should make that a separate point. You can find extrema. Actually, scratch that. I want to make that a bit more definite. All extreme values of a function occur at critical points or endpoints. And I want to stress that word point. It does have to be a point. If you've come to a place where your function is discontinuous for some reason and has no defined point there, then that can't be a maximum or minimum value because it's not a set point. All right, a couple of examples of working with this. I'll get myself a new page. Although, my technological genius, I might leave myself with that last statement there, because that's a good one. Although, getting fancy now. Woohoo! So if I take a look at example 4 from page 194 of your textbook, we're given a function f of x equals 1 over root 4 minus x squared, and we're asked to find extreme values. Find the extreme values of f of x. Oh, focus, that's good times. So, I need to look at critical points or endpoints. Now, one thing you will notice here is my x values cannot be bigger than 2 or less than negative 2. There is a diagram of this function on page 195, but basically x can't be bigger than 2 or less than negative 2, and it can't be equal to 2 or negative 2 either, because then I'd have division by 0. So the domain of this thing, it's worth pointing out, well, I'll use the set notation for this. x has to be within negative 2 to 2, non-inclusive. So I do not have solid endpoints, which means I don't have endpoints that I can check to see if I've got a critical value. So that means I can only look at critical points, places where my derivative either doesn't exist or is equal to 0. So that means I'm going to need to look at the derivative of this thing, and I might restate f of x as 4 minus x squared to the negative 1/2. I think that's going to make my life a little bit easier. So then the derivative of this, if I use my chain rule properly, should be bring the power down, leave the argument alone, reduce the power by 1, and then multiply by the derivative of what's in there. With some simplification, the negative 2 and the negative 1/2 multiplied together would cancel each other out, and I would have x over the square root of 4 minus x squared cubed. Good times. So, critical point. That's going to be where this derivative either doesn't exist or equals 0. Now, regardless of all that mess on the bottom, the only place this derivative is going to equal 0 is when x equals 0, because of the numerator. So f prime of x equals 0, and x equals 0. Now, f prime of x does have places where it doesn't exist, and that's going to be when I'm dividing by 0 in the denominator. So when x equals plus or net minus 2. However, it's worth noting these are not in the domain of the function. Therefore, we don't have to worry about those as far as critical points go. So this is our only possible extreme value on the function. So, is this a maximum or a minimum? I know that f of 0 is going to equal 1 over root 4 minus 0, or 1/2. If I try a couple of other points around this, f at 1, for instance, would equal 1 over root 4 minus 1, which is 1 over root 3. Root 3 is smaller than 2, therefore 1/2 is the smaller of these numbers. And f of negative 1 is going to do the same thing, 1 over root 4 minus 1, which equals 1 over root 3. F of 0 is less than f of 1. And f of 0 is less than f of negative 1. I think I just got some mail. Therefore, f of x has an absolute minimum at x equals 0, specifically at 0 and 1/2. So, how do I know that's an absolute minimum? First of all, my function is going to be continuous everywhere in this domain. There's no place where I get any division by 0 problems or anything like that. So for every x between negative 2 and 2, this is continuous. Furthermore, my extreme values have to happen at a critical point or an endpoint. There are no endpoints to this, so I can only get an extreme value at the critical point. There is only one critical point, which means there is only one local maximum or minimum. And since there's only one, and by the extreme value theorem, there's got to be an absolute maximum or minimum somewhere in here, then that's got to be an absolute value, an absolute maximum or minimum. Okay, I'll do one more quick example, and we'll leave it for there. Once I do, this one's got the piecewise function in it, which I know all the kids these days love. So this will be example 5 from page 196. Let's have a little more space there. And this is to find extreme values of minus x squared, or sorry, minus 2x squared, when x is less than or equal to 1, and x plus 2 when x is greater than 1. It is worth noting that this is going to be a continuous function. Focus. So for 1, at x equals 1, the left side of this function is going to be 5 minus 2 or 3. The right side would approach 1 plus 2 is 3. Since they approach the same value, and there's no other place that this could be discontinuous, this function is continuous everywhere. Ooh, there comes my focus. I'm hoping my next line will make that better. Bear with me. So I need to find critical points. Again, there are no endpoints stated for this. I'll cheat a little bit. Really? Not going to give me that even either? Thanks for that. Okay. Focus. Thank you. So I need to look at the derivative of this piecewise function. This derivative is going to equal negative 4x for x values less than 1, and 1 for x values greater than 1. I just took those from the derivatives of the two parts of the piecewise function. Notice that I haven't included x equals 1 anymore. That's because the derivative approaches different values as you come to 1 from the left or from the right. So therefore, the derivative itself does not exist at x equals 1, which is kind of important for us to talk about critical points. So, f prime of x equals 0. That's certainly not going to happen on the right side of this, but on the left side, it does happen when x equals 0. 0 or x equals 0. And as we just mentioned, f prime of x does not exist at x equals 1. It's worth pointing out that the graph of this shape, which is also shown on page 196, but it looks a terrible straight line. Something like this. So this would be what we've been calling a corner. So it is a place where the derivative doesn't exist. And this is also where I have a local maximum here at x equals 0. Alright. So I have, well, I should get my statements too. When x equals 0, my original function, working on the left side, negative 5 minus 0, or 5. At 1, I'm still working with the left side of the statement, and it's 5 minus 2, or 3. And it's worth also pointing out, neither of these is an absolute maximum or minimum, because my function continues on this way, and continues on this way. So I have a local maximum at 0 and 5, and a local minimum at 1 and 3. Okay, that's about all I have to say about absolute values, or not absolute values. Extreme values of functions, maximum, minimum values. While we are still in a phase of trying to figure out exactly how we're working going forward, I can't technically assign any work. If anybody wanted to practice a few things, some suggested things you can try would be here. For your interest. All right. That is about all I have to say about that for now. Stay safe, everybody.